Hello everyone, this is Dr. Hopkins. Welcome back to our series of videos for 106. Today we're going to talk about the solubility product and solubility of insoluble ionic compounds. And actually, I want to kind of narrow this down. We're not talking about the solubility of just any molecule, we're doing just ionic compounds. And so an ionic compound, or a salt, when you dissolve it in water, it dissociates. So for example, if we had sodium nitrate, we have sodium nitrate solid, we put it in water, it dissociates into the cation, sodium, and the anion, NO3 minus, or nitrate. For ionic compounds that are soluble, so the ones that dissolve in water, the dissociation is 100%. We just assume that they go to completion, so that's the reason why in the above example we have an arrow and not an equilibrium. If we have an ionic compound that's insoluble, then we know the level of dissociation, or the amount of dissociation is predicted based on the equilibrium constant, which in this case we call the solubility product, or KSP. So we write the same reaction. So for magnesium hydroxide, for example, which is an insoluble salt or ionic compound, we have our solid. Now we have an equilibrium because it's not 100%. And then we have our cation and our anions. And in this case, the KSP, if you look it up, is 8.9 times 10 to the minus 12. So if you look at that, that's a very small equilibrium constant, which means it's favoring the reactants. In other words, mostly this will stay as solid. There's very little magnesium and hydroxide produced. And so how do we know if we have an insoluble ionic compound? Well, one way we can do it is we can use the solubility guidelines, and you can look them up in any general chemistry book. You can look them up in our general chemistry book. It's typically something that's taught in the first semester of the 105 course. And what they are is just a set of algorithms. So you say, well, if we have a group 1 cation or an ammonium cation, the compounds are soluble, always. If we are hydroxides, if we have a hydroxide as our anion, they're all insoluble except when they are coupled with a group 1 cation or ammonium cation, and so forth. And you can go on and say the sulfides are insoluble and nitrates are soluble except these conditions, and halogens or halides are mostly soluble except if it's with silver, and so forth. So there's various kinds of sets of rules that you can go through and say, hey, if this is what it is, you can predict solubility. And it's a nice little table, and it's easy to do. The other way to know if you have an insoluble ionic compound is look up and see if there's a KSP. So if it has a KSP, that means it's insoluble. That means it's an equilibrium. So what we're going to do at this point is we're going to use KSP and determine the actual solubility of an insoluble, quote unquote, salt. And we're going to use our example of magnesium hydroxide. So let's figure out what's the solubility, the concentration of magnesium 2 plus when we add magnesium hydroxide to water. All right, so now we have our problem set up. We've got magnesium hydroxide, solid, added to water, so it's going to dissociate into magnesium 2 plus and 2 OH minuses, both aqueous. And we have a KSP, which was 8.9 times 10 to the minus 12. I forgot to write that down. So if we were to write this equilibrium expression, it would be the concentration of the products. And then we square the OH minus because of the 2, right? And it would be divided by reactants, but since the reactant is a pure solid, it divides away. So we're left with, that's our KSP. So now what we need to do is set up an ice table, which is the reason why I never really specified how many grams of magnesium hydroxide I added to the water. So in other words, we don't care. And see, so initially we're going to say we're going to add it to pure water. So our initial concentrations of both of those are 0. And then this is plus x. This is plus 2x, right? So our coefficient translates into our algebra, and then we have x and 2x, and then we plug those in, and actually, let's erase that. And that would be 8.9 times 10 to the minus 12 equals x times 2x squared, which is 4x cubed, okay, because you square the 2x. And then we divide through by 4 and solve for x, which is 1.3 times 10 to the minus 4. And since x is our concentration of, or is the equivalent of our magnesium 2 plus concentration, that means the magnesium 2 plus solubility is 1.3 times 10 to the minus 4 molar. So no matter how much magnesium hydroxide we add to the water, that's going to be our concentration. Now that we've gone through and solved the KSP to figure out our concentration of magnesium, and we know it's pretty small, if we wanted to, could we increase the solubility of magnesium by adding additional magnesium hydroxide? And I think I've addressed this, and the answer is basically no, because pure solids don't factor into the equilibrium. We could dump a ton of magnesium hydroxide into our water, and all it would do is sit at the bottom. It would not increase the concentration of magnesium one bit, because the concentration of magnesium is dictated by the equilibrium constant, which is dictated by delta G. So it's a thermodynamic function, not a concentration function. All right. So if that's the case, if we wanted to increase the concentration of magnesium 2 plus, how could we do that? Well, if you remember the reaction, we're generating magnesium 2 plus and OH minus. In Le Chatelier's principle, if we remove if we remove products, more reactants will react. So if we have OH minus, that's a base. We just got done probably taking way too much time talking about acids and bases. So if we were to add an acid, it would react with the OH minus, generate water, and then more of the magnesium hydroxide would have to dissolve to correct and make the correct equilibrium. So if we added acid, we could make it more soluble. So if we wanted to make magnesium hydroxide soluble in water, we just need to add acid. So what do you think would happen if we added hydroxide to the water or to this solution? Well, if we add product, Le Chatelier's principle say we'll shift back to reactants and we would generate more solid. So we would reduce the solubility of magnesium in water in that case. All right, so here's kind of an aside, precipitation reaction. So if we're looking at, if we have two soluble ionic compounds, we mix them together to get an insoluble ionic compound, that's called a precipitation reaction. It's kind of the definition of precipitation reactions. So let's take an example of one that could be a potential precipitation reaction. So magnesium chloride, we'll assume that it's solid. Most halides are. If we went through the solubility rules, we'd know. Sodium hydroxide, remember the solubility rules said that is soluble. So those are two soluble salts. We put them in water and they're going to completely dissociate. So I've written out what they dissociate into. Now, I don't have the stoichiometry right yet. We'll adjust that in a minute. And then those are going to float around and run into each other. So the sodium could run into hydroxide. Well, we already know that it dissociates, so it's not going to do anything. It could run into chloride. Sodium chloride is also soluble. It's a soluble salt. So that's not going to do anything. So those will stay in solution. The magnesium, when it runs into chloride, of course, we already know that it dissociated from the first place, so there's no big deal. Magnesium could run into hydroxide. Now, we've just done a KSP problem where we know magnesium hydroxide is not very soluble. So anytime the magnesium runs into two hydroxides, it forms a precipitation or a solid. So the combination that's insoluble is our magnesium hydroxide. So we would write the molecular equation. Here we have it balanced with the right stoichiometry. We'd have one magnesium chloride, two sodium hydroxides generating a magnesium hydroxide, and two sodium chlorides. Now, there's a lot of extra information in this equation. So what we want to do is let's write out the complete ionic equation. So we're going to dissociate anything that should be dissociated. So everything on the left side is dissociated. And only this insoluble salt is not dissociated on the right-hand side. And then you'll notice that the sodium and the chloride are the same on both sides. That makes them spectator ions and not really important because they're not changing in this reaction. So we can get rid of them, and our net ionic equation for a precipitation reaction is our cation and our anions forming our salt. And that's always the case. And that's the most important thing to do, is to write the net ionic equation for these kind of reactions. And you also notice that's actually the reverse of the KSP reaction. So the reverse, 1 over the KSP. So the equilibrium constant for this would be something on the order of 10 to the 13, 10 to the 12, whatever it might be. So it's fair to write this with an arrow if we're just considering our equilibrium constant. So the takeaways from this video are that soluble ionic compounds completely dissociate. This is something you probably should have learned last semester. I know we did a lab on that. Insoluble ionic compounds are going to dissociate according to our equilibrium constant. And we can look up our equilibrium constant in tables or determine it based on delta G's, which we know how to do. And we can form an insoluble salt by mixing two soluble salts together. It's called a precipitation reaction. If one of the combinations of cations and anions ends up being an insoluble ionic compound, which we can determine based on solubility guidelines or a table of KSPs. So until next time.